Welcome to a quiet corner of the sleepy scientist channel where we explore the world not as it seems, but as it is. A world of hidden patterns and silent forces. Tonight, we begin a journey not along a familiar riverbed carved deep into the earth, but high above, in the boundless blue. We are setting out to trace the course of the most powerful rivers on earth. Rivers that flow not with water, but with vapor. Rivers that have no banks yet shape our coast. Rivers that are entirely invisible yet dictate the fate of landscapes and lives below. These are the rivers in the sky. Before we cast our gaze upward, I'd be curious to know where you are listening from. Perhaps you're in a place where the rain is gently falling against your window, or maybe under clear skies, unaware of the aerial currents flowing miles above. If you find a sense of wonder in these hidden stories, I would be so grateful if you would gently tap the like button and subscribe. To those of you who are already part of this community, thank you. Your presence is the steady current that allows us to explore these deep waters together. And a small note, I hope this foray into the atmosphere brings a sense of calm fascination, not restless worry. But if it does keep you awake, perhaps you'll listen to the wind outside with a new, deeper understanding. So how can a river exist in the sky? The idea seems like a paradox, a thing of myth. We are taught that rivers are defined by their channels, their sources, their mouths meeting the sea. They are bound by gravity, flowing definitively downhill. But the atmosphere has its own geography, its own logic. It is a fluid, just as the ocean is a fluid, and within it currents form. Some are gentle breezes, others are jet streams, powerful, ribbon-like winds that circle the globe. And sometimes, within this complex dance of air, something extraordinary coalesces. A long, narrow, concentrated conveyor belt of moisture. A channel of saturated air that can stretch thousands of kilometers across the ocean, from the tropics to the poles. It carries an almost unimaginable volume of water vapor, funneling it with a relentless purpose. This is an atmospheric river. Think of it not as a river of clouds, but as a river that becomes clouds. It is the essential ingredient, the potent source. When this invisible vapor-laden current is forced upwards by a mountain range, by colliding with colder air masses, it has no choice but to release its immense cargo. The vapor cools, condenses, and transforms into the torrential rain and heavy snow that can define a season, or break a drought, or unleash a flood. These sky rivers are the true giants of our planet's water cycle. While they may be invisible to the naked eye, we see their footprints everywhere. In the deep snowpack of the Sierra Nevada that provides water for millions, in the filled reservoirs that sustain communities through dry summers, and in the heartbreaking news reports of towns submerged, mudslides tearing down hillsides, and rivers bursting through levees, they are a force of both creation and destruction, a duality written into their very nature. For much of human history, we experienced their effects without ever knowing their name. A seemingly endless parade of storms would arrive from the ocean, and we could only attribute it to a particularly potent winter or the whims of weather. We saw the rain, but not the river that delivered it. But now, with the eyes of satellites and the minds of scientists, we can finally map these unseen currents. We can trace their origins in the warm, humid air above the distant tropics and forecast their journey across the Pacific or the Atlantic. We can begin to understand their rhythms, their power, and their profound influence on our world. This journey will take us from the silent, vast expanse of the open ocean to the frantic operations of emergency rooms, from the cutting edge of supercomputer forecasting to the ancient stories of great floods that echo through time. We will learn how to read the language of the sky, to listen for the whisper of the wind that speaks of the river it carries. So let us begin at the beginning, not with a splash, but with a breath of warm, moist air. Let us understand how these rivers form, and how they flow, silent and unseen, above us all. In our last moments together, we introduced the idea of a river flowing through the sky, a concept that feels almost mythical. But to truly understand it, we must first clear away what it is not. For the human eye, accustomed to seeing the world in shapes and forms, it is the easiest thing to look at a massive storm system on a weather map and mistake it for our sky river. But the two are profoundly different. An atmospheric river is not a storm. It is not a hurricane, not a cyclone. Those are the engines of chaos, spinning vortices of wind and cloud. They are the tempests. An atmospheric river, by contrast, is something more focused, more streamlined. It is not the engine itself, but the fuel line. A long, narrow, concentrated channel that feeds moisture into the storms, that supplies the rain and snow to weather systems along its path. So if it is not a cloud and not a storm, what exactly is it? Imagine the atmosphere not as empty space, but as a vast, deep ocean of air. Within this ocean, currents flow. Some are broad and slow, others are tight and fast. An atmospheric river is one of these currents, but it is a current not defined by its speed, but by its incredible saturation. It is a plume of intensely moist air, a stream of vapor so dense that it stands out dramatically from the drier air surrounding it. Think of it like the Gulf Stream in the Atlantic Ocean, a powerful, identifiable current with properties distinct from the water around it, flowing within the greater body of the ocean. The atmospheric river is the Gulf Stream of the sky. It has a beginning, a middle, and an end. It has a specific direction and flow. And most importantly, it carries a phenomenal cargo. The scale of these features is what truly defies everyday experience. A single, well-defined atmospheric river can be over 1,500 kilometers wide. That is the distance from London to Vienna. But its true astonishment lies in its length. These rivers can stretch for thousands upon thousands of kilometers, often carrying moisture from the warm, humid tropics all the way to the polar regions. They are continental in their reach, yet ribbon-like in their focus, and within this long, narrow corridor, the concentration of water vapor is almost unimaginable. The entire plume, if you could somehow squeeze the vapor out of it, often carries a volume of water vapor equivalent to the flow at the mouth of the mighty Amazon River. Let that settle for a moment. The Amazon, the largest river on Earth by volume, disgorging a colossal torrent into the Atlantic. Now picture that same amount of water, not as a liquid, but as an invisible gas, flowing through the atmosphere in a stream that is, by comparison, remarkably narrow. This is the sheer staggering power we are discussing. A river in the sky rivaling the greatest river on the ground. Its structure, revealed to us by satellite technology, is both simple and elegant. It is not a shapeless blob of humidity. It has a core, a region of the most intense moisture transport, much like the fastest flowing current in the middle of a terrestrial river. This core is where the winds are strongest and the vapor is most concentrated. It is the heart of the sky river, and just like a river on land, it has boundaries. They are not made of earth and stone, but of sharp gradients in humidity. On one side of this invisible wall, the air is incredibly rich with moisture. On the other side, it is remarkably dry. This boundary is not always neat. There are eddies and swirls at the edges, but it is distinct enough for our instruments to trace its path with stunning clarity from space. This is the central truth. We are not looking for a river made of water or even a river made of clouds. We are looking for a river made of potential. It is a latent force, a suspended promise of rain and snow. It is water held in the arms of the wind, waiting for the moment to be released. It is the architect of our weather, the silent supplier that determines whether a passing, low-pressure system will be a gentle shower or a historic deluge. To understand this distinction between the storm and the river that feeds it is to take the first step in reading the sky's deepest secrets. It allows us to see the atmosphere not as a chaotic mess, but as a system of organized flowing patterns. Patterns that bring life, and patterns that with a terrible and awesome force can also take it away. To understand the journey of a sky river, we must first learn the geography of its world. A world without mountains, without valleys, at least not in the way we know them. The geography of the atmosphere is a topography of temperature, of pressure, of humidity. It is a landscape written in the invisible, a map of forces that guide the winds and shepherd the vapors across the empty expanses of the globe. Under the intense gaze of the sun, the ocean's surface warms and water molecules, energized by this heat, break free from the liquid embrace of the sea and ascend into the air as vapor. This is the wellspring, the source lake for our aerial rivers. It is here, over the warm waters near the equator and the subtropics, that the air becomes deeply, profoundly saturated. It is the first gathering of drops in a vast, impending current. But this moist air does not simply rise and fall in place. It is caught in the grand, planetary-scale circulation of the atmosphere. It begins to move, flowing poleward, away from the equator. And as it travels, it is shaped and guided by the powerful, high-altitude winds known as the jet streams. These jet streams act like the continental divides of the sky, creating the slopes down which the rivers of vapor will flow. The most famous of these aerial waterways, the one we have come to know as the Pineapple Express, is a prime example of this global geography. Its journey is a long and purposeful one. It gathers its strength in the warm, humid air around the Hawaiian Islands and the tropical Pacific. Then it is caught by the prevailing winds and swept northeastward, thousands of kilometers across the open ocean, until it finally reaches the western shores of North America. It is a non-stop flight of moisture, from the lush tropics to the rugged temperate coasts. But this is not the only river in the sky. It is merely one of the most prominent in a constant global cycle. Similar rivers flow across the Atlantic, carrying moisture from the Caribbean and the Gulf of Mexico towards Western Europe. The United Kingdom and Norway are often the recipients of this aerial gift, their green landscapes shaped by these regular, moisture-laden deliveries. In the southern hemisphere, mighty rivers form in the Tasman Sea, streaming towards the coast of Australia and New Zealand. Others flow from the Amazon basin southward, impacting the southeastern parts of South America. They are a universal phenomenon, these conveyor belts in the troposphere, tirelessly redistributing the planet's moisture from where it is abundant to where it is needed. The paths they take are not random. They are dictated by the permanent and semi-permanent features of the atmospheric landscape. High-pressure systems act like massive, stable plateaus, blocking and diverting the flow. Low-pressure systems, with their counterclockwise winds in the northern hemisphere, can siphon moisture from these rivers, pulling them northward and wringing them out against mountain ranges. The journey of a sky river is a perilous one. Throughout its long voyage, it is constantly losing strength. Its moisture is shed as scattered showers or evaporated back into the drier air around it. Only the strongest, most focused filaments of moisture survive the long transit across the ocean basins to make landfall with their power intact. It is a testament to the immense volume of water vapor they carry at their source that any of it arrives at all. When they do finally reach a coastline, the true interaction begins. The invisible geography of the atmosphere meets the solid, unyielding geography of the Earth. The river in the sky must now contend with the mountains on the land. And it is this meeting, this collision between the fluid and the fixed, that writes the final dramatic chapter of the river's story, transforming its silent journey into thunderous impact. To map these sky rivers is to understand the planet's circulatory system for water. It connects the equatorial heat to the polar ice, the ocean's abundance to the continent's thirst. It is a geography that is always changing, yet forever following the same ancient paths dictated by the spin of the earth and the heat of the sun. A hidden map drawn in vapor and wind that guides the very breath of the world. Of all the rivers that flow through the sky, one has captured our imagination more than any other. It has a name that sounds less like a weather phenomenon and more like a festive holiday train. But do not let its cheerful name fool you. The Pineapple Express is the most famous and often the most potent atmospheric river in the world. It is a recurring character in the climate story of the West, a deliverer of both salvation and ruin. Its name tells us its story. Pineapple for its tropical origins in the warm waters around the Hawaiian Islands. Express for its direct, relentless, and powerful journey across the Pacific Ocean. It is not a meandering stream. It is a non-stop moisture freight train, and its terminus is often the mountainous coastline of North America, from British Columbia down through California. The journey begins gently enough. Under the Pacific sun, water evaporates from the ocean's surface, saturating the lower atmosphere. This warm, humid air is then caught by the larger-scale winds of the atmosphere. It is gathered up, organized, and funneled into a narrow, concentrated channel. Imagine a garden hose lying in the sun, filling with warm water. Now imagine that hose is 1,500 miles wide and thousands of miles long. This is the scale we are speaking of. The river lifts its moisture from the tropical air, and the prevailing winds begin to push it eastward and northward. For days, this colossal plume travels across the open ocean, a river of vapor flowing steadily between layers of drier, cooler air. From space, it is visible to our satellites as a long, tendril-like band of intense water vapor, a bright, sinuous finger pointing from the tropics directly toward the coastline. It is a breathtakingly beautiful and orderly phenomenon, but the true nature of the Pineapple Express is revealed not over the ocean, but upon landfall. When this warm, saturated river of air encounters the western edge of the continent, it is forced to rise. The Sierra Nevada, the coastal ranges, the Cascades, these magnificent mountain walls stand directly in its path. And just as a terrestrial river crashes into a dam, the sky river crashes into the mountains. The air has no choice but to ascend. As it rises, it cools. And as it cools, the vapor it holds so densely must condense. It transforms from an invisible gas into a multitude of visible water droplets, forming clouds. And then it releases its immense cargo. The result is a phenomenal concentrated deluge. Rain falls not for hours, but for days. At the highest elevations, where the air is coldest, this moisture falls as feet of heavy, wet snow. This is the dual soul of the Pineapple Express. In its benevolent guise, it is the essential lifeline for the West Coast. It is the storm that ends droughts, the system that builds up the critical snowpack in the mountains that will slowly melt through the spring and summer, feeding reservoirs and providing water for millions of people and vast swaths of agriculture. A strong Pineapple Express season can erase a water deficit and fill the landscape with a deep, vibrant green. It is the difference between plenty and parched, but in its fierce guise, the Express becomes something else entirely. When the river of vapor is too intense, too persistent, or arrives on already saturated ground, the same mountains that wring out the life-giving water become the architects of catastrophe. The rain falls too fast for the soil to absorb. It runs off, cascading down slopes, swelling creeks into torrents, and turning rivers into monsters that overflow their banks. The warm nature of the system presents a particular danger in the winter. It can bring a rain-on-snow event where warm rain falls onto a deep, existing snowpack. The rain melts the snow incredibly rapidly, unleashing a devastating double dose of water that can overwhelm any system designed to contain it. It is this version of the Pineapple Express that has caused some of the most historic and destructive floods on record, carving canyons, swallowing towns, and reshaping the land itself. To witness a true Pineapple Express event is to experience weather on a scale that feels biblical. The rain does not fall in drops, but in continuous streaming sheets. The wind is often warm and fierce. The sound is a constant roaring white noise that can last for days, a testament to the unimaginable volume of moisture passing overhead. The Pineapple Express is a powerful reminder that we are connected to distant parts of the planet in intimate and profound ways. The humidity born of warm Hawaiian waters becomes the rain that falls on California's vineyards, the snow that blankets Oregon's forests, and the floodwaters that challenge British Columbia's valleys. It is a permanent atmospheric feature that ties the fate of ecosystems and civilizations across a vast expanse of ocean. It is not merely a weather pattern, it is a recurring character in a long, ongoing story. A story of abundance and of peril flowing silently and inevitably through the sky, from the land of pineapples to the land of peaks and valleys. We have spoken of rivers in the sky, of currents of vapor flowing unseen above us. But to understand their true power, we must move from the poetic to the tangible. We must ask a simple yet staggering question. How much water are we truly talking about? The concept of water vapor can feel light, ethereal, insubstantial, a mist, a fog, a wisp of cloud. But this is an illusion. Water is heavy. A single gallon of water weighs over 8 pounds. A single cubic meter of volume about the size of a small kitchen oven weighs a metric ton. And an atmospheric river does not deal in gallons or cubic meters. It deals in Mississippi rivers. The numbers used to describe these systems are so vast that they defy everyday comprehension. Meteorologists measure the strength of an atmospheric river by a metric called integrated vapor transport, or IVT. It calculates the total amount of water vapor being moved horizontally by the wind within a column of the atmosphere. The values for a significant atmospheric river are astronomical, but let us translate this from the language of science into the language of image. Imagine the Amazon River, the greatest river on Earth by volume. At its mouth, it discharges an almost unimaginable amount of water into the Atlantic Ocean every single second. Now picture that same colossal flow, not of liquid water, but of water vapor suspended in the air. A single, well-developed atmospheric river can often carry a volume of water vapor equivalent to 15 to 20 times the average flow of the Mississippi River at its mouth. At their most extreme, they can truly rival the flow of the Amazon itself. This is not a river in the sky. This is a flying Amazon. This immense weight of water has a profound physical effect. All that water vapor has mass. This means an atmospheric river has immense weight. The column of air within a strong atmospheric river can be 2.5 to 3 times heavier than a column of dry air. This weight creates a significant dip in atmospheric pressure at the surface, which in turn strengthens the winds that are funneling the moisture along. It is a self-reinforcing system. The heavier, moisture-laden air fuels the very winds that are driving it forward. To grasp the energy contained within this system, we can think in terms of power. The latent heat energy released when all that vapor condenses into rain is staggering. A major atmospheric river can release latent heat energy equivalent to the total electrical generation capacity of the United States, continuously for several days. In more visceral terms, the condensation energy can sometimes be compared to the explosive yield of multiple atomic bombs every second. This is the energy that fuels the ferocity of the storms it supplies. This is the engine behind the historic rains and hurricane-force winds. And when this flying river meets a mountain range, the effect is like turning on a fire hose pointed directly at the slopes. The term meteorologists use is orographic enhancement, but that sterile phrase belies the violence of the process. The mountains act as a mechanical wrench, forcibly squeezing the vapor from the air. The result? Precipitation rates can become almost unbelievable. It is not uncommon for a strong atmospheric river to dump inches of rain per hour over mountainous terrain. Over the course of a multi-day event, a single mountain slope can receive 5, 10, even 15 inches of liquid equivalent precipitation. This is the weight of the Sky River made manifest. It is no longer vapor. It is a solid, crushing mass of water falling from the heavens, seeking the path of least resistance back to the sea. This quantification changes our perspective entirely. That gentle mist we started with, that single drop on a leaf, is a part of this incomprehensible whole. The soothing sound of rain on the roof is the audible evidence of a meteorological phenomenon of epic power happening directly overhead. It transforms the sky from an empty expanse into a landscape burdened with unimaginable weight. It makes the wind something that doesn't just blow, but that carries. It makes the air itself something that can be full to bursting. The next time you see a forecast for a pineapple express or an atmospheric river, know that it is not just a forecast for rain. It is a forecast for the movement of entire seas across continents. It is the announcement that a flying Amazon is making landfall, carrying with it the dual promise of life-giving water and the raw, terrifying power of nature itself. It is the weight of water given form and purpose, flowing silently above us all. In our last moments, we stood beneath the awesome, terrifying weight of a sky river unleashed. We felt the potential for destruction in its immense power. But to see these phenomena only as agents of catastrophe is to miss half of their story, and perhaps the more profound half. For these same atmospheric rivers are not merely destroyers, they are fundamentally life-givers. They are the primary architects of water security for entire regions of the world, and the silent partners in maintaining some of our most precious ecosystems. There exists a delicate, crucial balance in the strength and frequency of their visits. They are the benevolent giants in the story of the West, the difference between a thriving landscape and a barren one. Consider the simple, vital reservoir. For cities and farmlands from California to British Columbia, these human-made lakes are the checking accounts for water, saved during the seasons of plenty to be spent during the long, dry summers. And what makes the largest deposits into this account? It is not the gentle winter showers or the occasional spring rain. It is the atmospheric rivers. These systems are responsible for up to half of the annual precipitation in some areas, and an even greater percentage of the water stored as snowpack in the high mountains, the nation's most critical natural reservoir. A single, well-behaved atmospheric river event in the heart of winter can erase a worrying water deficit. It can add feet of snow to the Sierra Nevada, the Cascades, and the Rockies. This snow is not just water. It is perfectly timed water. It sits, frozen, through the winter and early spring, then slowly melts as the weather warms, trickling down through watersheds and into reservoirs precisely when demand begins to rise. This slow release is the rhythm that entire water management systems are built upon. Without these sky rivers, this rhythm falters. The result is drought. The reservoirs shrink. The soil cracks. The forests become parched and stressed. We have seen this story unfold in recent years, a tense waiting game for a deliverance that comes only from the sky. The absence of atmospheric rivers is a crisis. Their return is a relief. Beyond the pipes and irrigation canals of our cities, these rivers in the sky are the lifeblood of natural ecosystems. The mighty coastal redwoods of Northern California, the tallest trees on Earth, are testament to this. They exist in their staggering grandeur precisely where they do because of a unique climatic recipe of summer fog and, crucially, winter deluges delivered by atmospheric rivers. These giants drink deeply from the storms, their shallow root systems absorbing the immense rainfall that soaks the forest floor. Further inland, the annual pulses of water from these events trigger extraordinary natural cycles. They fill seasonal wetlands, creating temporary oases for migratory birds on journeys of thousands of miles. They flush sediment and nutrients through river systems, revitalizing estuaries where fresh water meets the sea, creating some of the most biologically rich nurseries on the planet. Salmon, struggling upstream to spawn, rely on these freshwater pulses to help them navigate and to ensure their eggs will have enough oxygenated water to survive. This is the delicate balance. The same phenomenon that can cause a river to burst its banks and scour a valley is also the same force that ensures the river has water in it to begin with. The line between a drought-busting rain and a catastrophic flood is astonishingly thin. It can depend on the temperature of the ocean where the river formed, the speed at which it is moving, the amount of moisture already held in the soil, and the precise angle at which it hits the mountain ranges. A region's relationship with atmospheric rivers is one of deep dependency and respectful anxiety. Water managers watch the forecasts for them with a mix of hope and trepidation. They hope for a series of nice ones, moderate, cold enough for snow, spaced out to allow the land to recover. They fear the big one, a warm fire hose blast aimed directly at a vulnerable watershed. This duality forces a profound shift in perspective.
We cannot wish them away.
To curse the atmospheric river is to curse the rain that fills our glasses and grows our food. It is to curse the snow that paints the mountains white and the rivers that run through our wild places. Instead, we must learn to understand them better, to see them not as unpredictable monsters, but as powerful, natural forces that have shaped the world we live in long before we built our cities in their path. They are the key to resilience in a world of increasing climatic uncertainty. Our challenge is not to defeat them, but to live within their rhythm, to capture their abundance without being overwhelmed by their power, to appreciate the delicate balance between the flood and the famine, and to respect the giant that brings us both. For days, a river of vapor has flowed thousands of feet above the ocean, silent, immense, and full of potential. It carries within it the essence of floods and the promise of snowpack, yet it remains just that, potential. For all its immense weight and power, an atmospheric river can journey vast distances without shedding a single drop. It is a suspended ocean, a held breath, so what causes it to finally exhale? What is the trigger that transforms this invisible current into a torrential downpour, converting its latent energy into the kinetic fury of rain and snow? The answer lies in a simple, inescapable law of physics. Air must rise. As warm, moist air is forced to ascend, it moves into regions of lower atmospheric pressure. It expands, and as it expands, it cools. Think of the air releasing the energy it used to hold those water molecules apart. This cooling is the key. There is a critical temperature, known as the dew point, where the air can no longer hold all its invisible water vapor. The vapor is forced to condense around microscopic particles in the atmosphere, dust, salt, pollen, pollution, forming countless tiny water droplets or ice crystals. These droplets coalesce, gathering into clouds, growing heavier and heavier until gravity can no longer hold them aloft. And then they fall. The trigger then is not a single switch, but a set of circumstances that force this great aerial river uphill. The most powerful and effective of these triggers is the unyielding hand of the land itself. This process is called orographic lift. When a moisture-laden atmospheric river slams into a mountain range, the land provides the ultimate upward shove. The air has nowhere to go but up and over the barrier. As it is forced violently upward along the windward slopes, it cools rapidly, condenses, and unleashes a tremendous amount of precipitation. This is why a single mountain range can have a lush, rainforest-like environment on one side and a dry, rain-shadowed desert on the other. The mountain acts as a colossal wrench, systematically squeezing the moisture from the sky river. The steeper the slope and the more intense the river, the more dramatic and concentrated the ringing out effect becomes. But mountains are not the only trigger. Sometimes the lift comes from a battle of air masses, a phenomenon known as frontal lift. Imagine the leading edge of an atmospheric river not as a clean line, but as a vast, sloping battlefield where two great armies of air meet. A mass of cold, dense air can act like a plough, sliding beneath the warmer, moist air of the atmospheric river and forcing it to rise over the top of the cold wedge. This forced ascent triggers the same process of cooling, condensation, and rainfall, often spread over a wider area than the focused deluge of a mountain range. There is a third, more large-scale trigger: convergence. Imagine two winds, not necessarily strong, but blowing directly toward each other. The air has nowhere to go at the point of meeting but upward. This convergence acts like a gentle hand pushing from below, encouraging the air to rise and begin the process of cloud formation. While not as dramatic as a mountain range, this process can help initiate and sustain the rainfall over flatter regions. Finally, there is low-level jet dynamics. The core of an atmospheric river is often accompanied by a powerful stream of wind just above the surface. When this jet of wind encounters an obstacle or a change in the landscape, even a gradual rise in terrain, it can be forced to ascend, again providing the necessary lift to unlock the precipitation. The character of the precipitation itself, whether it falls as a life-giving rain, a destructive deluge, or a massive snowfall, is determined by one final, critical factor: the temperature profile of the entire atmospheric column. If the air is cold enough from the cloud base all the way down to the ground, the condensed water will freeze and fall as snow, building up the precious snowpack. But if a layer of warm air intrudes, it can melt the falling snow into rain, even at high elevations. This rain-on-snow event is one of the most feared triggers of all, as it delivers a devastating 1-2 punch: the immediate deluge of rain, plus the rapid melting of the existing snow, unleashing a double volume of water onto the landscape below. So, the release of the Sky River's payload is not a matter of chance. It is a precise physical reaction. It is the inevitable consequence of a journey that ends with an ascent. The mountain, the cold front, the converging winds, they are the catalysts. They provide the lift that turns the key, unlocking the vast, suspended ocean within the river of vapor and unleashing its power upon the world below. The trigger is pulled not by an unseen hand, but by the immutable laws of physics and the ancient, enduring shape of the land. There is a precise and terrifying moment when a blessing becomes a catastrophe. It is a threshold, invisible until it is crossed. For an atmospheric river, this is the moment when the life-giving rain transforms into a destructive flood. The same water that quenches the thirst of the land and fills the reservoirs begins to overwhelm it. The same system that ends a drought now threatens to erase the landscape. This transition is not a matter of fate, but of physics. It hinges on a delicate and brutal arithmetic between the sky and the ground. The first variable is intensity. A gentle rain, even over many hours, can be absorbed by the soil. It seeps down to recharge aquifers. But an atmospheric river does not often deal in gentleness. It can unleash rainfall rates of an inch or more per hour. When rain falls this hard and fast, the ground simply cannot keep up. The surface becomes sealed, the pores in the soil clogged with the very water they are trying to absorb. The rain stops infiltrating and starts flowing. It becomes runoff, sheeting across streets, lawns, and hillsides, seeking the nearest gutter, drain, or creek with terrifying efficiency. The second variable is duration. An atmospheric river is not a passing thunderstorm. It is a fire hose aimed at the same spot for 24, 36, sometimes 48 hours or more. This relentless duration is what breaks the land's back. Even a moderately intense rain, if it continues without pause, will eventually saturate the soil completely. The earth becomes a soaked sponge that can hold not a single drop more. Every new raindrop that falls thereafter has no choice but to become immediate runoff, adding its volume directly to the rising waters. But the Sky River does not act alone. Its impact is dictated by the third, and perhaps most crucial variable, the antecedent conditions, what was happening on the ground before the rain began. Imagine the land is a bank account. A series of previous smaller storms may have already made significant withdrawals, leaving the soil's moisture account nearly full. When the atmospheric river arrives, it makes a massive deposit into an account with no capacity. The result is an instant overflow. Now imagine a more perilous scenario, a landscape recently scarred by wildfire. The intense heat has baked the soil, making it hydrophobic. It actually repels water. The protective layer of vegetation that once slowed the rain's impact is gone. The land is now primed for disaster. When the Sky River opens, the water does not soak in. It flashes across the barren, hardened ground, picking up ash and debris as it goes, morphing into a lethal slurry of mud and rock that races downhill with devastating speed. These debris flows are among the most destructive forces in nature, burying everything in their path. The final trigger in the transition is the temperature.
A warm atmospheric river, the infamous Pineapple Express, brings a special kind of danger.
It can cause a rain-on-snow event. Warm rain falls onto a deep, existing snowpack. The rain delivers its own volume of water, while simultaneously working like a blowtorch, melting the snowpack at an accelerated rate. This unleashes a double volume of water, the rain itself and the melted snow, in a horrifyingly short period. The watershed is hit with a 1-2 punch. It has no hope of weathering. This is when the creek becomes a torrent. The river bursts its banks. The water begins to reclaim its ancient floodplain, flowing through neighborhoods that were built where it once naturally wandered. The gentle gurgle of a storm drain becomes a throaty roar. The road becomes a river. The park becomes a lake. The transition is not a slow, gradual rise. It is often sudden and explosive. It is the moment the soil's patience breaks. It is the moment the capacity of a culvert is exceeded. It is the moment the levee, stressed beyond its design, first begins to seep. It is a fundamental shift in the relationship between the water and the land, from cooperation to conquest. The flood is the Sky River's will, finally and forcefully imposed upon the earth. It is the inevitable result of an imbalance in the equation when the atmosphere's offering of water vastly exceeds the land's ability to receive it. The benevolent giant has been pushed too far, and its life-giving touch has become a devastating blow. The river in the sky has at last found its way back to the earth, not as a blessing but as a deluge. The story of an atmospheric river does not end where the sky meets the land. In many ways, it is there that the most critical chapter is written. For the land is not a flat, passive canvas upon which the rain uniformly falls. It is an ancient, complex sculpture of rock and soil with its own peaks and troughs, its own ridges and channels. This topography, the shape of the land itself, is the final and most decisive editor of the Sky River's message. It determines who will receive a gentle shower and who will bear the brunt of a cataclysm. The most powerful interaction is between the river in the sky and the mountains on the earth. This relationship is one of forced confrontation. As the warm, saturated air of the atmospheric river is driven against a mountain range, it has no escape. It is compelled to rise. This forced ascent, known as orographic lift, is the most efficient precipitation machine on the planet. The effect is brutally simple. The windward side of the mountains gets a deluge. As the air is shoved up the slopes, it cools rapidly, wringing out its immense moisture load in a concentrated, torrential outburst. The higher the mountain, the more lifting it provides, and the more rain or snow is squeezed from the sky. This is why a place like California's Sierra Nevada or Washington's Olympic Mountains can receive staggering annual rainfalls, places that exist in a state of perpetual, dripping green magnificence, all thanks to the topography that forces the sky to yield its water. But the mountain's role is not just vertical, it is also directional. The specific orientation of a mountain range acts like a spotlight, focusing the atmospheric river's energy. A range that runs perpendicular to the incoming moisture, a north-south range like the Sierra facing a west-to-east flowing river, presents a solid, unbroken wall. This maximizes the lift across a wide area, creating a blanket of extreme precipitation. A range that runs at an angle will receive a more glancing blow, distributing the rainfall differently. The shape of the land, therefore, writes the blueprint for the storm's impact before the first drop even falls. Once the water is wrung from the sky, the topography takes over again, now as a conductor of floodwaters. The rain that falls on the steep upper slopes does not linger. It immediately begins to run downhill, following the relentless pull of gravity.
Innumerable tiny trickles merge into rivulets, rivulets into creeks, and creeks into streams.
The intricate network of canyons, gullies, and ravines that cut through the landscape act as a natural plumbing system, funneling this runaway water into increasingly larger arteries. This is where the second act of the flood unfolds, in the beauty valleys. A river valley is literally the place where water is meant to go. It is the lowest point, the gathering place for all the runoff from the surrounding hill slopes. During an atmospheric river event, these valleys become conduits for a catastrophic convergence. Water from hundreds of square miles of mountainous terrain is funneled into a single main stem river. The geometry is unforgiving. Imagine the valley as a funnel. The wide upper catchment area, the entire mountain watershed, collects a massive volume of water. The valley itself is the narrow spout. When the flow into the wide top exceeds the capacity of the narrow bottom, the water has nowhere to go but up and out, overtopping the river's banks and inundating the floodplain. The very feature that makes valleys ideal for human settlement, flat ground near a freshwater source, is what makes them profoundly vulnerable. We have built our towns and cities in the path of this ancient, hydraulic convergence. The third topographical player is the foot of the mountains, the alluvial fans and coastal plains. When raging, debris-laden rivers exit steep canyons and hit the flatter ground, they slow down abruptly. They lose the energy to carry their heavy load of sediment, rocks and debris. They drop it all, fanning out and often clogging their own channels. This process can cause the water to abruptly change course, spreading out in unpredictable and destructive sheets across the plain. Burying everything in its path under mud and rock, the land, therefore, is not a victim of the Sky River's fury.
It is an accomplice.
The mountain lifts and concentrates the rain. The slopes gather and accelerate the runoff. The valleys funnel and focus the flood. The shape of the earth takes the broad, diffuse threat of the atmospheric river and sharpens it into a precise and devastating point. To understand flooding is to read the topography. It is to see a quiet valley and understand that it is a drain for the mountains above. It is to see a steep canyon and know it is a chute for runaway water. It is to look at a town nestled against a beautiful range and recognize that it sits quite literally in the exit path of the Sky River's storm. The flood is not just water falling from the sky. It is water being guided, directed, and amplified by the silent, immutable sculpture of the land itself. For most of human history, the arrival of a great storm was a matter of surprise. People could read the signs in the aching joints, the behavior of animals, or the thickening of the clouds, but the true scale and intent of a sky river remained a mystery until it was already upon them. It was a force that moved in silence, high above the realm of human perception. Today we have learned to read the signs. We have built a global network of eyes and ears that listen to the whispers of the atmosphere, allowing us to trace the birth and journey of an atmospheric river days before it makes landfall. The science of forecasting these events is a delicate and brilliant art, a symphony of technology and intuition. It begins, quite literally, with a view from heaven.
Satellites are our most powerful sentinels.
Geostationary satellites, fixed high above a single point on the globe, provide a constant, mesmerizing movie of the planet's cloud cover. They show us the swirling dance of weather systems. But to see the river itself, we need different eyes. We use microwave and water vapor satellites. These don't just see clouds, They peer through them, measuring the amount of water vapor held in the invisible air below. They can map the long, narrow, tendril-like plumes of moisture snaking across the ocean, revealing the structure, the concentration, and the direction of the atmospheric river long before any clouds have even begun to form over the coast. From this vantage point, the river is no longer invisible. It is a bright, distinct signature painted across the map. But to truly understand its character, we must take its measurements from within. This is the work of a fleet of weather balloons. Twice a day, at hundreds of locations around the world, these sturdy white balloons are released into the sky. As they soar through the atmosphere, they radio back precise data on temperature, pressure, humidity, and wind speed at every level of their ascent. This vertical profile is the equivalent of a doctor's blood test for the atmosphere. A single balloon launch off the coast of California can tell forecasters not just that an atmospheric river is coming, but how deep it is, how saturated, and how strong the winds are that are driving it. It reveals whether the river is warm or cold, which dictates whether it will bring rain or snow. For the most critical events, we send in the storm hunters. Aircraft reconnaissance flies directly into the heart of the emerging river. The famous hurricane hunters of the U.S. Air Force Reserve and NOAA do not just chase hurricanes. They also fly precise patterns through developing atmospheric rivers over the Pacific. They deploy instruments called drop-sondes, small, parachute-equipped cylinders jammed with sensors that are released from the plane. As they fall through the river of vapor, they transmit a continuous stream of data, painting a high-resolution, vertical picture of the moisture and wind. This is like sending a deep-sea probe into an ocean current. It provides the ground truth that satellites can only infer, and it dramatically improves the accuracy of our forecasts. All this data from the satellites, the balloons, the aircraft, is a torrent of numbers, a digital snapshot of a fluid global atmosphere. This is where the final, and perhaps most crucial piece of technology comes in. The computer model. These are not simple programs. They are virtual worlds, complex mathematical simulations of the entire planet's climate system. Supercomputers ingest the millions of data points and run them through equations that govern the physics of the atmosphere, the laws of motion, thermodynamics, and moisture. The models then project this virtual atmosphere forward in time. They attempt to simulate how the atmospheric river will evolve. Will it strengthen or weaken? Will it stall or accelerate? Will it hit the coast head-on or glance off? Forecasters don't rely on just one model. They consult an entire ensemble of them, each with slightly different starting assumptions. They look for where the models agree, forming a consensus forecast, and they pay close attention to where they disagree, which highlights the uncertainty and the potential for surprise. The final forecast is a masterpiece of synthesis. It is the human forecaster, a skilled interpreter, sitting before these arrays of satellite imagery, balloon data, and model projections. They blend the hard numbers with their own understanding of local topography and the quirky tendencies of certain weather patterns. They ask, do the models understand how this river will behave when it hits the Santa Lucia Mountains? Is the cold air offshore being underestimated? This is how a forecast is born. It is not a guess. It is the product of a global collaborative effort to perceive the invisible. It is the act of translating the silent language of the wind, the vapor, and the pressure into a map, a timeline, a warning. It is our attempt to listen to the sky river's murmur days in advance, to understand its intent, and to whisper its plans to those living in its path. We have learned to read the signs not in the clouds but in the silent, vapor-laden currents that flow above them. The true measure of our relationship with atmospheric rivers is not written in the calm between storms, but in the frantic hours of their arrival. And it is in this chaos that we see two very different stories unfold. The story of a storm we saw coming and the story of one that took us by surprise. The difference between them is the difference between managed disaster and outright catastrophe. It is a tale of two storms. The forecasted fury, our first story, begins days in advance. Over the Pacific, satellites identify the telltale plume of moisture. Weather balloons launched from Guam, Hawaii, and the West Coast sample the air, confirming its strength. The supercomputer models, ingesting this data, begin to sing in chorus. They plot a consistent path, a strong atmospheric river aimed like an arrow at Northern California, arriving in 60 hours. This consensus triggers a well-rehearsed machine. The National Weather Service issues a series of increasingly specific alerts, from a simple hydrologic outlook to a definitive flash flood watch. Meteorologists on television and online use clear, urgent language. This is not a typical storm. They speak of rainfall rates, river levels, and snow levels with precision. This clarity gives the most precious resource: time. In the foothill towns, public works crews are dispatched to clear storm drains of autumn leaves. Sandbags appear at the entrances to vulnerable businesses. Emergency managers pre-position swift water rescue teams. Schools announce closures a day in advance. On the radio, the message is constant: stay off the roads tomorrow. If you live in a flood-prone area, know your evacuation route. The river arrives exactly as predicted. The rain is torrential, a deafening roar on rooftops that lasts for 36 hours. Creeks swell, but they do not overtop their banks unexpectedly. A levee is stressed, but a crew is already there monitoring it. The river floods, but into a designated floodplain, not a neighborhood. There are road closures, some property damage, and undeniable anxiety. But there is no panic. The community is hunkered down, watching and waiting. The storm is a severe event, but it is a managed event. The accurate forecast acted as a shield, allowing society to brace for the impact. The unseen hammer, our second story, begins differently. The models are in disagreement. Some hint at a potent system, but others weaken it or push it far out to sea. The forecast is low confidence, a maybe. The messaging is muddled. Keep an eye on the forecast later this week. There is no clear call to action. Unbeknownst to the models, the atmospheric river is undergoing rapid intensification over the ocean. A subtle shift in the jet stream strengthens it. A pool of especially warm ocean water feeds it more vapor. It becomes a fire hose that none of our instruments fully grasp until it is too late. It arrives not as a forecasted event, but as a shock. The rain begins at midnight, harder than any forecast had suggested. By 2 a.m., weather offices scramble to upgrade warnings to the highest category, but most of the world is asleep. The first sign of trouble for many is the sound of water where it shouldn't be, a gurgling through the floorboards, a lake forming in the backyard. Then, the chaos begins. Cars are caught on suddenly inundated roads, drivers trapped. A creek, never before a threat, explodes from its channel, swallowing homes in minutes. Mudslides, unanticipated because the risk was never communicated, bury roads. Emergency services are overwhelmed, responding to calls rather than preventing disaster. The community is not hunkered down. It is blindsided. People flee in the dark with only the clothes on their backs. The damage is not just to property, but to the very sense of security. The storm was not just weather. It was an ambush. The thin line. These two tales are separated by a thin line, a few degrees of model uncertainty, a slight error in the predicted track, a failure to capture a key atmospheric process. The river in the sky was the same physical phenomenon in both cases, a conveyor belt of immense moisture. But its impact was dictated entirely by our ability to see it coming. The well-forecast storm is a testament to our technological advancement. It shows that when the chain of data, modeling, and communication works, we can stand face to face with a natural giant and withstand its blow. It is a story of resilience built on knowledge. The surprise storm is a humbling reminder of the atmosphere's infinite complexity and our own limitations. It shows that for all our satellites and supercomputers, nature can still deliver a knockout punch we never saw coming. It is a story of vulnerability. Together, these two stories define the high-stakes challenge of living in the path of the sky rivers. Our safety does not just depend on building stronger levees or higher walls. It depends, first and foremost, on our ability to read the signs in the sky ever more clearly, to extend the window of warning, and to ensure that the message of a coming fury reaches every ear in its path. For the difference between the two tales is not the water that falls from the sky, but the knowledge that precedes it. We have learned to map the sky rivers and to understand the ancient grammar of the land that directs their fury. But there is a third and increasingly dominant force in this equation: us. Human activity has rewritten the landscape, and in doing so, we have often redrawn the map of our own vulnerability. We have, at times, become unwitting architects of our own disaster, turning the natural threat of a flood into a human-amplified catastrophe. The first and most profound change is urbanization. We have paved the world. We have covered vast expanses of absorbent earth with a skin of impermeable concrete, asphalt, and rooftops. This transformation creates what hydrologists call an urban watershed. In a natural landscape, when rain falls, the soil acts like a sponge. It absorbs a significant amount, releasing it slowly to groundwater and streams. But in a city, the sponge is gone. The concrete skin cannot drink. Instead, it shepherds the water. Every parking lot, every street, every roof becomes a tributary, channeling rainfall with horrifying efficiency into storm drains and gutters. These drains then act like a superhighway system for water, funneling it at lightning speed into the nearest creek or river. What was once a slow, natural process of absorption and gradual release is now a rapid, concentrated flush. The result is that urbanization dramatically shortens the time it takes for a flood to begin. It also magnifies its peak. A river that might have risen slowly over days in a natural setting now spikes to a dangerous crest in a matter of hours under the relentless, efficient runoff from the city's concrete landscape. We have replaced the sponge with a slide, and the atmospheric river, with its intense rainfall rates, is perfectly designed to send a catastrophic volume of water down it. If urbanization removes the sponge, then wildfire fundamentally alters its chemistry. A landscape recently scorched by a major fire is perhaps the most dangerously primed terrain for a flood imaginable. The intense heat of the fire bakes the soil, creating a waxy, water-repellent layer just below the surface. This phenomenon, called hydrophobicity, means the ground no longer absorbs water. It actively repels it. At the same time, the fire has consumed the vegetation, the trees, shrubs, and grasses whose roots once held the soil in place and whose leaves broke the fall of the rain. The land is left bare, covered in a layer of ash and devoid of any natural obstacles. When an atmospheric river moves over a fresh burned scar, the consequences are apocalyptic. The rain does not soak in. It immediately sheets off the hydrophobic soil, picking up immense quantities of ash, soil, rocks and charred debris as it flows. This is no longer a flood of water. It is a debris flow, a fast-moving, lethal slurry of mud and rock that has the consistency of wet concrete and the destructive power of a freight train. These flows can barrel down canyons with little warning, burying roads, homes, and entire communities under feet of mud. They are among the most destructive forces on Earth, and they are a direct product of the 1-2 punch of fire and flood, a cycle that is becoming increasingly common and severe. Our interventions in the rivers themselves have also had complex consequences. We build levees to protect existing communities, but these walls can create a false sense of security, encouraging further development on the very floodplains we know are dangerous. And when a levee fails or is overtopped by an event larger than it was designed for, the results are catastrophic. as the water that was meant to be slowly accommodated across a wide plain is now unleashed as a sudden, concentrated torrent. We have, in essence,
Stacked the deck against ourselves.
the atmosphere provides the immense moisture, the topography directs it, and our own alterations to the land, the paving of the sponge and the creation of the hydrophobic slides ensure that this moisture is converted into devastating runoff with terrifying speed and efficiency. This is not nature's fury alone. It is a collaborative disaster, one in which we have played a leading role. The floodwaters that rage through a city street or the debris flow that buries a home are not just products of the Sky River. They are also products of our choices. They are a reminder that we are not passive inhabitants of this landscape, but active participants in its reshaping. To live safely in the path of these aerial giants requires us to not only understand the weather and the land, but to honestly confront the consequences of our own footprint upon it. The solution lies not just in better forecasts, but in wiser building, thoughtful land management, and a profound respect for the natural pathways of water. We track atmospheric rivers now with satellites that see every droplet of vapor, and we measure their fury with radar and rain gauges. Our records, meticulously kept, span decades, but to truly understand the power and potential of these sky rivers, decades are merely a blink. To comprehend their full might, we must learn to read a much older archive. We must listen to the stories told in mud, in tree rings, and in stone, stories of ancient flows that make our modern storms seem like whispers. This is the work of paleoclimatology, the detective work of Earth's deep past, and the evidence it uncovers reveals that the sky rivers of history were not merely events. They were epochs of water that reshaped continents. Our first witness is the sediment core. Scientists drill deep into the beds of quiet lakes, marshes, and floodplains. What they pull up is a timeline, a layered record of the past. In normal years, fine, slow-setting silt and organic matter drift down, creating a dark, thin layer. But then there are the anomalies, thick, coarse bands of sand and gravel, interrupting the gentle accumulation. These are the flood layers. They speak of catastrophic events when raging rivers carried a pulverized landscape far out of their banks and into these calm basins. In places like California's Santa Barbara Basin, where ocean sediments accumulate without disturbance, these layers are perfectly preserved. The cores reveal a stunning history. For thousands of years, the most extreme flood events, the ones that deposited the most spectacular layers, occurred almost exclusively during periods when atmospheric rivers were stronger and more persistent. These bands of sediment are the geologic fingerprints of prehistoric sky rivers, their strength and frequency varying with the changing climate over centuries. Then there are the tree rings.
A tree is a patient scribe recording each year of its life in the width of a ring.
A wide ring signifies a year of plentiful water and good growth. A narrow ring, a year of drought. And sometimes scientists find something more dramatic. Scars. The incredible force of a flood carrying massive debris. Boulders, logs, battering rams of rock can literally sandblast the bark off trees growing on riverbanks. The tree survives, but it bears a scar in its rings, a record of that traumatic year. By dating these scars in ancient buried trees, scientists can pinpoint the precise years of catastrophic flooding centuries ago, building a chronology of megastorms long before human records began. The most haunting testimony comes from the megastorms themselves. The detective work has pieced together events of almost mythical proportions. One in particular stands out, the Great Flood of 1861-62. This was a historical event, but its scale was paleoclimate in magnitude. A series of atmospheric rivers, one after another, pummeled California for 43 days. The Central Valley turned into an inland sea 300 miles long and 20 miles wide. Sacramento was submerged under 10 feet of water. The state legislature had to row to its sessions. The state was bankrupted and 1 in every 8 homes was destroyed. It was a catastrophe born of the sky, but the paleoclimate record suggests this was not a unique event. Sediment cores show evidence of even larger floods over the past 2 millennia. And then we go back even further to a time beyond human memory. Scientists have identified evidence of truly apocalyptic events, super megastorms that occurred every few centuries. These were sequences of atmospheric rivers that lasted not for weeks, but for months, unleashing enough water to reshape entire landscapes, carving canyons, and depositing immense layers of sediment that geologists can still see today. These ancient flows teach us a humbling lesson. Our modern instrumental record, the one we use to plan our cities and design our infrastructure, is woefully short. It has captured a relatively quiet period. It has not captured the full, terrifying potential of the sky. We build for the 100-year flood, but the paleo record speaks of 500-year floods, 1,000-year floods. These were not freaks of nature. They were part of the natural rhythm of a volatile climate system. The atmosphere has always known how to open the taps to a breathtaking degree. This deep time perspective changes everything. It means that a catastrophic flood is not a modern anomaly caused by climate change. Though our warming world may be increasing their frequency, it is a recurring feature of this planet. The potential for a deluge that dwarfs our modern experience has always been there, latent in the climate system, waiting for the right alignment of ocean heat and atmospheric steering. The ancient mud and the scarred trees are our warning. They tell us that the great floods of our history were not the worst possible events. They were merely the worst we have witnessed. The sky rivers have flowed with far greater power in the deep past, and they will again. They remind us that we do not live on a placid, predictable planet, but on one that has always been capable of profound, violent change. Our history is but a brief chapter in a very long and very wet book. For all of human history, the weather was a deeply local and deeply mysterious affair. We could feel the wind shift, see the clouds gather, and sense the pressure drop in our bones. But we could only guess at the patterns unfolding beyond the horizon. The birth, life, and journey of a storm were stories we had to piece together from the ending, only understanding the plot once the rain was already upon us. That all changed when we learned to rise above the clouds, when we placed our eyes in the heavens. The satellite's view revolutionized our understanding of the planet and of atmospheric rivers most of all. From the lonely, wind-swept perspective of Earth orbit, these invisible currents were suddenly revealed in their full, breathtaking grandeur. We could finally see the river. The first satellites gave us the godlike view of geostationary orbit. Positioned over a fixed point on the equator, 22,000 miles above the planet, these spacecraft take a continuous picture of nearly an entire hemisphere. From here, we can watch the weather unfold like a grand, slow-moving ballet. We see the swirling commas of low-pressure systems, the vast spirals of clouds, and the majestic procession of weather systems marching from west to east. We can see the context, the stage upon which the atmospheric river plays its part. But to see the river itself, we needed more than pictures of clouds. We needed to see the invisible. This is where the true magic lies. Microwave satellites are our seers. They don't just look at the tops of clouds, they peer through them. They measure the natural microwave energy emitted by water vapor molecules in the air below. By measuring this energy, they can precisely quantify the amount of moisture in a column of the atmosphere, painting a picture of its density and concentration. What appears to our eyes as a featureless bank of clouds is revealed by the microwave sensor as a long,
narrow, brilliant plume of intense moisture, a bright,
snaking river of vapor against a darker, drier background. This is the first true mapping of the sky river's anatomy. Then there are the water vapor satellites. These instruments map the distribution of vapor in the upper and middle levels of the troposphere. They create stunning ethereal images of the atmosphere, where shades of white and grey don't represent clouds but gradients of humidity. In these images, the atmospheric river appears as a distinct, ghostly filament, a long, flowing tendril of white against the darker, drier air. It looks less like a weather system and more like a vein in a vast celestial body, a vital channel in the global circulatory system of water. The most advanced satellites now provide a three-dimensional view. Using radar and LiDAR, they can profile the atmosphere, telling us not just how much moisture is present, but how it is stacked from the ocean surface all the way to the stratosphere. They can measure the height of the cloud tops, the size of rain droplets, and the ferocity of the winds that are driving the river forward. This allows scientists to calculate that critical metric, integrated vapor transport, IVT, the total amount of water vapor being moved by the wind. It transforms a beautiful image into a precise, quantitative forecast. This constant global vigil allows us to do something once thought impossible. Track an atmospheric river from cradle to grave. We can watch it gather its strength over the warm waters of the subtropics, see it become organized and funneled by the jet stream, and trace its relentless path across thousands of miles of open ocean. We can watch it intensify, weaken, or split apart. We can see days in advance exactly where it is aimed. This is no longer just observation. It is prophecy. The satellite's view has demystified the sky river. It has taken a phenomenon of myth and terror and made it a known, measurable quantity. We no longer have to wonder what is coming from over the horizon.
We can see it.
We can measure its strength, predict its path, and understand its intent. Yet for all the cold, hard data it provides, the satellite's view has also deepened the poetry of these phenomena. There is a profound beauty in those images. The delicate yet powerful tendril of white vapor arcing gracefully across the deep blue marble of our planet. It is a visual testament to the elegance and interconnectedness of the Earth's systems. The satellite is our silent partner in the sky. It is the unblinking eye that watches over the ocean's expanse, that sees the rivers flowing through the void, and that whispers their secrets back to us. It has given us the ultimate perspective, allowing us to finally see the world not as a collection of isolated weather events, but as a single, dynamic, and breathtakingly beautiful whole. We have lifted the veil and found not chaos, but a majestic, flowing order written in vapor and wind. From space, satellites map the river of vapor with serene, silent precision. From the ground, radars scan its leading edge. But there is a crucial piece of the puzzle that can only be gathered from within the heart of the beast itself. To truly know an atmospheric river, you must fly into it. This is the mission of the hurricane hunters. But their quarry is not always a spinning cyclone. Increasingly, they fly towards a different kind of monster, long,
Narrow and deceptively serene from a distance.
but holding within it the same potential for catastrophic release. The aircraft is a workhorse, a ruggedized Lockheed WC-130J Hercules. It is built not for comfort, but for endurance and strength, designed to pound through the worst turbulence the atmosphere can muster. Its skin is peppered with strange probes and sensors, and its belly is modified to release small, cylindrical instruments into the void below. This is not a passenger plane. It is a flying laboratory, and its crew are scientist airmen on a data-gathering raid into the sky. The mission begins hours before the flight with a forecast. The scientists and meteorologists at the National Oceanic and Atmospheric Administration, NOAA, and the Air Force Reserve identify a promising or threatening atmospheric river developing over the Pacific. They plot a course. Their goal is not to avoid the worst of the weather, but to find it. They aim to fly a series of precise lines, like a lawnmower pattern, directly through the most intense core of the moisture plume. As the aircraft approaches the river, the world outside the windows transforms. The clear blue sky gives way to a vast, featureless grey. Then the turbulence begins. It's not the violent punching jar of a thunderstorm, but a constant, rough shaking, a prolonged, aggressive rattling that speaks of immense energy and powerful winds. The plane is being buffeted by the very river it has come to measure. Inside the crew is a picture of focused calm. The pilot's hands are steady on the yokes, making constant micro-corrections to hold the course. The flight meteorologist monitors the real-time data streaming in from the external sensors: wind speed, wind direction, temperature, pressure, humidity. They are watching the anatomy of the river unfold on their screens. Then comes the critical moment. The order is given: ready on the dropsonde. A dropsonde is a marvel of miniaturization. It is a slender cylindrical instrument package about the size of a large water bottle, attached to a small parachute. At the command, a crew member loads it into a launch tube and releases it. The sonde drops free of the aircraft and its parachute deploys, slowing its descent towards the churning ocean miles below. As it falls, the dropsonde becomes a data bloodhound. It radios back a continuous stream of information, a vertical profile of the atmosphere's every secret. It measures the temperature and humidity from the top of the river down to the sea surface. Most importantly, it precisely tracks the wind speed and direction at every level using GPS. This vertical slice is the gold standard. Satellites see the river from above, but the dropsonde feels it. It tells scientists exactly how the river is structured, where the fastest winds are, how saturated the air is at different altitudes, and where the river's core is most potent. A single flight can release dozens of these sondes, building a detailed three-dimensional map of the entire atmospheric river system. The experience inside the plane is one of surreal immersion. They are flying blind, encased in a world of grey. The only sense of motion comes from the instruments and the constant vibration. They are, for all intents and purposes, sailing a metal ship through a current of vapor and wind, a current that is thousands of feet deep and hundreds of miles wide. They are inside the very phenomenon they are trying to understand. The data they gather is immediately radioed back to forecasting centers on the mainland, is fed directly into the supercomputer models. This is the game changer. Before these missions, models had to make educated guesses about conditions over the vast, data-sparse ocean. The dropsonde data replaces guesswork with ground truth. It can dramatically improve a forecast, narrowing the uncertainty about where the river will hit and how intense the rainfall will be. It turns a low-confidence forecast into a high-confidence warning, gifting precious hours for preparations on the ground. These flights are a testament to a specific kind of courage. It is not the courage of sudden action, but of sustained, deliberate focus in the face of elemental power. It is the courage to seek out the storm, to willingly fly into the unknown, not for conquest, but for understanding. They do not fly to conquer the river in the sky. They fly to know it, to measure its pulse, to chart its boundaries, to listen to its breath. And in doing so, they translate its raw, chaotic power into a language of numbers and maps. They are the translators between the human world and the immense, fluid world of the atmosphere, turning the roar of the wind into a whisper of warning that can save lives and protect communities. They journey into the river so that those of us on the ground know when to seek higher ground. For much of our history, a forecast for an atmospheric river was a binary thing. It was coming, and it would bring rain. But this simple yes or no failed to capture the vast spectrum of possibilities. Was it a storm that would gently end a drought, or one that would wash away a town? The lack of a common language left everyone, from scientists to water managers to the public, struggling to understand the risk. We needed a way to give the Sky River a volume knob. We needed to categorize its voice from a whisper to a scream. This is the purpose of the atmospheric river scale. Developed by meteorologists, it is a simple yet profound tool that translates the complex physics of these systems into a clear, 5-point scale of potential impact. It doesn't just measure the storm, it interprets its intent. The scale is elegantly built on two pillars: the amount of moisture the river is carrying and how long it is going to stall over a region. These two factors, intensity and duration, are multiplied together to give a final ranking. From AR1 to AR5, and AR1 is primarily beneficial. Think of it as a gentle, steady rain. It is the drought buster, the garden waterer, the snowpack builder. It is the kind of storm that soaks quietly into the earth, replenishing aquifers and filling reservoirs without causing any fuss. It is the welcome guest, and AR2 is mostly beneficial but also somewhat hazardous. This is a moderate storm. It brings significant needed rainfall, but it might cause some minor roadway flooding or quick rises in small streams. The benefits still far outweigh the problems, but it carries a hint of its own power. An AR3 is neutral. This is the balance point. This storm delivers a strong dose of precipitation that is valuable for water supply, but it also brings a real, measurable risk of flooding, especially in urban areas or recently burned hillsides. It is a mixed bag, a storm that demands attention and respect. It is neither purely good nor purely bad. Then we cross a threshold. An AR4 is mostly hazardous. The scale has now tipped. While it may still provide some water supply benefits, they are overshadowed by the high probability of significant flooding. This is where rivers threaten to overflow their banks, where debris flows are likely, and where communities need to activate their emergency plans. The Sky River is no longer a benefactor. It is a threat, and AR5 is primarily hazardous. This is the extreme event. This rating is reserved for the legendary storms, the ones that shape history and redefine flood maps. These are the events that unleash catastrophic, life-threatening flooding and widespread damage. An AR5 is a worst-case scenario, a storm where the primary mission is no longer water storage, but survival. But the scale's true genius lies in its understanding of context. It knows that the same volume of water can be a blessing or a curse, depending on where and when it falls. The scale incorporates a location-specific modifier. An AR3 storm falling on a severe drought is an unqualified blessing. That same AR3 storm falling on already saturated ground in a wildfire burn scar could be instantly upgraded to an AR4 or even AR5 in its local impact. The scale is not rigid. It is fluid, intelligent, and responsive to the landscape it will affect. This common language has transformed how we talk about, prepare for, and respond to these events. When a forecaster can now say an AR4 is expected to make landfall tomorrow, it conveys an immediate, understood level of risk. It tells emergency managers what level of response to trigger. It tells the public whether they need to simply carry an umbrella or whether they need to evacuate their home. It has also helped us move beyond the simplistic idea of a good storm or a bad storm. The AR scale acknowledges that these systems are inherently both. They are the most important source of water for the West, and also its greatest weather-related hazard. The scale allows us to have that nuanced conversation. We can now yearn for an AR2, prepare for an AR3, and fear an AR5. It is a tool that brings clarity to chaos. It gives us a way to measure the immeasurable, to categorize the uncategorizable. By giving the Sky River a number, we are not diminishing its power. We are beginning to understand it. We are learning to speak its language, not so we can command it, but so we can listen to its warnings and appreciate its gifts. It is the language of impact, a vocabulary of water and wind that allows us to finally hear the difference between a sigh of relief and a scream of warning.
A flood recedes.
The waters drain away, the mud is scraped from the streets, and the broken levees are rebuilt. To the casual eye, the landscape heals. Green shoots push through the silt, and the river returns to its banks seemingly chastened. But the land does not forget, and neither do the people who live upon it. The memory of a great flood is etched into both the earth and the human spirit. a permanent record of the day the Sky River fell. The land itself is the most faithful historian. It keeps a silent, stony ledger of past inundations. Walk along a river canyon and look up, high above the current waterline. You might see a strand line, a distinct, linear deposit of sediment, gravel and debris clinging to the cliff face. This is a high water mark, a permanent notation left by a flood that may have occurred decades or even centuries ago. It is the land's way of recording the river's highest reach, a ghostly watermark from a forgotten deluge. In the quiet soil of a floodplain, the history is written in layers. Core samples extracted from the ground reveal a storybook of past events. Layers of dark, organic, rich soil tell of centuries of calm growth. Interrupting these are thick, coarse bands of sand and gravel, the calling cards of ancient catastrophes. Each band is a chapter where the river burst its confines and laid down a new, brutal layer of its own making. Geologists can read these strata like tree rings, dating the great floods that shaped the valley long before any town was built there. This geological memory dictates the very shape of life. The ecosystems are built around this rhythm of flood and drought. Riparian trees like willows and cottonwoods are adapted to have their roots submerged and scoured. Their seeds are designed to germinate in freshly deposited silt. The entire riverside forest is a community that remembers the flood's creative power, its reliance on the occasional chaos for renewal, but the memory is not held only in the soil and the trees. It is held in the stone and concrete of human settlement. The height of a levee is not an arbitrary number. It is a calculation based on the memory of the last big flood, plus a margin of safety, a hope that the future will not exceed the past. A bridge is built not for the gentle flow of today, but for the remembered torrent of yesteryear. Its arches are raised high to clear the driftwood and debris that the river carried the last time it rose in anger. Every town that has known a great flood has its own geography of memory. There is the high water mark on the old library wall, a brass plaque or a painted line that shows the astonishing height the water reached. It becomes a local landmark, a place where parents point and tell their children a story that feels like a myth. The water was up to here, they say, and the child looks up, trying to imagine their familiar street transformed into a raging canal. This shared memory becomes woven into the culture. There are the oral histories, the stories passed down from grandparents. The winter of the great flood, they begin. And the tale unfolds of rowboats down Main Street, of neighbors helping neighbors, of the strange quiet that followed the storm. These stories are a form of social DNA encoding lessons of resilience and community. This collective memory shapes behavior. It is why some farmers refuse to build their homes on the lowest part of their land, choosing a slight rise instead, a decision passed down through generations based on a flood that happened 100 years ago. It is why the old-timers in a coastal town know which roads are the first to wash out and where the safest evacuation route lies. This is instinctual knowledge born of lived experience and inherited narrative. Yet memory is a fragile thing. As generations pass, the direct link to the disaster fades. The high watermark becomes just a curious line on a wall, its story losing its urgency. New people move to town, drawn by the beauty of the river, unaware of its dormant power. Development pushes further into the floodplain, the old warnings forgotten in the pursuit of a beautiful view. This is the constant, quiet tension in flood country between the land's long memory and humanity's short one. The land remembers every flood, every surge of the Sky River, and waits for the next. A community's resilience depends on its ability to keep that memory alive, to build not just on the soil, but on the stories. To live in the path of the sky, rivers is to live with this ghost, The memory of the flood is a shadow that lingers in the sunshine, a whisper in the rustle of the leaves. It is a reminder that the landscape we see is temporary. The river has been higher, and it will be again. The memory is a kind of armor and a guide. It tells us where to build, how to build, and, ultimately, when to step back and let the ancient water flow through its old, remembered path. In the logic of a stable world, drought and flood are opposites. They are the two ends of a pendulum's swing. One, a terrible absence, the other, a terrifying excess. We have built our world on this logic, expecting the pendulum to swing gently between them with a predictable rhythm. But we are no longer in a stable world. The pendulum is now being swung by a stronger, more erratic hand, and at times it seems to strike both sides at once. This is the new paradox. In a warming climate, the same regions are becoming both more prone to profound drought and more vulnerable to catastrophic flood. The same community can find itself praying for rain one season and weeks later praying for it to stop. This is the phenomenon of climate whiplash, and the atmospheric river is its primary weapon. The mechanism of this paradox is cruel in its elegance. A warmer atmosphere is a thirstier atmosphere. It holds more water vapor, accelerating evaporation from soils, rivers, and reservoirs. It leads to earlier snowmelt in the mountains and longer, more intense dry seasons. This is the engine of mega drought, not just a bad dry spell, but a years-long, deep-seated aridification that stresses ecosystems and drains water reserves to critical levels. But that same warmer atmosphere, now bloated with extra moisture sucked up from a heating ocean, also provides more fuel for the storms that do arrive. When conditions align for an atmospheric river to form, it is now carrying a heavier load. It's the difference between a standard garden hose and a fire hose being turned on a landscape that has been baked dry for years. This is where the whiplash occurs. The very ground that is most in need of a slow, gentle, soaking rain is the least capable of receiving it. The drought itself sets the stage for the flood. The sun-baked soil becomes hard and hydrophobic. It repels water like pavement. The vegetation that once held the earth in place is withered and sparse. When the fire hose of an AR4 or AR5 level atmospheric river is turned on this landscape, the water cannot infiltrate. It does not recharge the aquifers or slowly fill the reservoirs. It immediately becomes devastating, erosive runoff. The land, desperate for a drink, is instead force-fed a deluge it cannot swallow. The result is a catastrophic flush, water that rages across the surface, carrying away the precious topsoil that the drought had already weakened, and causing flash flooding that is both sudden and severe. The drought has not been broken. It has been catastrophically interrupted. This creates an impossible challenge for water management. Our infrastructure was designed for the old pendulum. Dams and reservoirs are built to capture a steady, predictable melt from a reliable snowpack. They are less effective at capturing a sudden, violent pulse of water that arrives all at once in the winter. The operators face a terrible choice: release water from a half-full reservoir to make room for the coming storm and risk worsening the drought if the storm veers away, or hold the water and risk the reservoir overtopping during the deluge, potentially causing a dam failure. It is a high-stakes gamble with the weather, and the rules of the game are changing faster than our infrastructure can adapt. This paradox also reshapes the very nature of the water itself. In the mountains, a warmer atmosphere means the precipitation from an atmospheric river is more likely to fall as rain, not snow, even at very high elevations. This robs the landscape of its natural, most efficient water storage system, the snowpack. Instead of a frozen reservoir that releases water slowly through the spring and summer, the water arrives all at once, in the winter, as an immediate flood risk. The feast is so colossal it cannot be stored, and the famine that follows can be even more severe because the snowpack bank is empty. We are moving from a climate dominated by snow to one dominated by rain, from a system of storage to a system of loss. This is the central, heartbreaking contradiction of our time. The same force that brings the water we desperately need to end a drought, the atmospheric river, is now often arriving in a form that is too intense to use and too destructive to ignore. The solution to the scarcity becomes the cause of the disaster. We can no longer think of drought and flood as separate problems. They are now two symptoms of the same fevered planet. They are the twin faces of a disrupted water cycle, a cycle that is now characterized by long,
agonizing stretches of want, punctuated by short,
violent episodes of overwhelming surplus. To navigate this new reality requires a new way of thinking. It demands that we build for both the drought and the flood simultaneously. It requires us to find ways to capture the fury of the deluge and save it for the depths of the dry times. It forces us to understand that the river in the sky will continue to flow, but its gifts are becoming more volatile, more extreme, and more paradoxical. Our survival will depend not on hoping for a return to normal, but on learning to dance in the dangerous space between the two. We have learned to see the sky rivers of the present. We can map their journeys, measure their might, and even fly into their hearts. But a pressing, urgent question now hangs in the air. What will they become? In a world growing warmer by the year, how will climate change reshape these colossal currents of vapor? Will we see more of them? Will they grow stronger? The answers are written in the fundamental physics of our planet, and they point toward a future where the sky river's dual nature, as both life-giver and destroyer, will be thrown into ever sharper,
more dangerous relief. The core of the prediction lies in a basic,
powerful law of atmospheric thermodynamics, the Clausius-Clapeyron relation. In simple terms, for every degree Celsius of warming, the atmosphere can hold approximately 7% more water vapor. Our planet has warmed and will continue to warm. This is not a hypothesis. It is a measured fact. This means the fundamental fuel for atmospheric rivers, water vapor, is increasing. The atmosphere is becoming a larger bucket, capable of carrying a heavier load. This doesn't necessarily mean there will be more atmospheric rivers. The processes that trigger their formation, the complex dance of high and low pressure systems, the meandering of the jet stream, may not become more frequent. Climate models are still working to understand the intricacies of these patterns. Some research suggests the number of events might even slightly decrease in some regions, but on this point, the science speaks with much greater certainty. While the number of rivers may change little, their intensity is almost certain to increase. The ones that do form will be juiced by a warmer world. They will be carrying a larger volume of moisture. Think of it not as more hoses, but as the same number of hoses now pumping at a higher pressure. This points to a future where the scale we learned about tilts toward the higher, more hazardous end. An event that might have been a strong AR3 in the 20th century could become a hazardous AR4 in the 21st. The legendary once-in-a-generation AR5 events, the true monsters, are projected to become more common. We are, in effect, turning up the volume on the Sky River's most powerful voice. The character of these events is also likely to change. A warmer atmosphere means the freezing level will be higher. More precipitation will fall as rain, even at high elevations. This dramatically increases the risk of the rain-on-snow events we fear, where warm deluges rapidly melt snowpack, unleashing devastating double volumes of water. The natural storage system of the mountains, the snow that holds water back for slow release, will be compromised. Replaced by immediate, overwhelming runoff, there is another, more complex shift that scientists are investigating: the potential for these rivers to stall. Some studies suggest that a warming Arctic may be weakening the jet stream, causing it to meander more and sometimes get stuck in large, wavy patterns. If an atmospheric river gets caught in one of these patterns, it could stall over a single region for days, like a fire hose aimed at the same spot on a wall, until it breaks through. The duration of these events is just as critical as their intensity. A stalled AR4 could unleash amounts of rain currently unimaginable, turning a serious flood into a continent-altering catastrophe. This intensification will not be felt equally across the globe. The already wet regions, the ones that rely on and are threatened by atmospheric rivers, will likely get wetter. The polarizing paradox of drought and flood will intensify. The arid regions on the edges of these storm tracks may be starved of even more precipitation, deepening droughts even as their neighbors are inundated. This is the future flow. It is not a prophecy of doom, but a physics-based projection. It is the logical consequence of adding more heat energy and more moisture to the climate system that creates these phenomena. The river in the sky is a central character in the story of climate change, and its role is being rewritten to be more extreme. This knowledge is not meant to paralyze us, but to prepare us. It makes the mission of forecasting, of building resilient infrastructure, and of rethinking water management more critical than ever. We can no longer plan for the storms of the past. We must design for the storms of the future, storms that will test the very limits of our dams, our levees, and our communities. The future of the Sky River is one of amplification. Its gentle rains may become rarer, its life-giving gifts may arrive in more violent, concentrated bursts, and its destructive power will likely grow. Understanding this is our first and most crucial step in learning how to live with the giant that flows above us, ensuring that its future chapters include both its life-giving water and our enduring resilience. The river's path is changing. We must have the wisdom to change with it. For millennia, we have stood as passive recipients of the sky's bounty and its wrath. We prayed for rain and fled from floods. But as our understanding has grown, so has our ambition. We have chosen to no longer merely endure the cycle of drought and deluge. We have decided to become architects, to design, to build, to intervene. Our goal, to capture the fury of the flood and transform it into the promise of the future. This is the great engineering challenge posed by the atmospheric river: how to tame the fire hose without wasting a single drop. Our most visible monuments in this endeavor are the dams and reservoirs. These are the giants of water management, the blunt instruments of control. A dam is a question posed to a river. You shall go no further until I allow it. The reservoir behind it is the answer, a massive artificial lake that interrupts the river's frantic rush to the sea. During an atmospheric river event, these reservoirs perform a delicate ballet. They must capture the tremendous surge of water, holding it back to prevent catastrophic flooding downstream. But they cannot fill too much too fast, for the weight of the water could threaten the dam structure itself. Operators must constantly balance the flood risk against the water supply need, making decisions with the lives of thousands in the balance. But the era of simply building bigger dams is largely over. The best sites are taken, and the environmental costs are high. So the new architecture is looking downward, into the earth itself. The concept of managed aquifer recharge, MAR, is a form of hydrological alchemy. It seeks to turn pavement into a sponge. The idea is to deliberately capture the torrential runoff from atmospheric rivers and spread it across large, permeable areas, old farm fields, specially designed basins, and parks, allowing it to percolate down and recharge the underground aquifers. These aquifers are nature's own massive storage tanks, holding far more water than any surface reservoir. By actively filling them during wet years, we create a savings account for the inevitable droughts. We are using the landscape itself as a living, breathing battery, storing the Sky River's energy not in concrete, but in stone. The architecture is also becoming smarter. The smart reservoir is a concept powered by data. Using the precise forecasts from satellites and hurricane hunter missions, water managers can proactively release water before a major atmospheric river arrives. This creates a reservation space within the reservoir, like clearing chairs out of a room before a big party. It's a calculated risk. You lose some water up front, but it dramatically increases the reservoir's capacity to capture the coming floodwaters, turning a threat into a captured resource. This is water management as a strategic game, played with the planet's own weather forecasts. In cities, the new architecture is about undoing the damage of concrete. Green infrastructure is a philosophy of distributed, small-scale intervention. It's about replacing impermeable surfaces with permeable ones. It's the construction of bioswales, green vegetated ditches that absorb and filter street runoff. It's the installation of rainwater cisterns that capture downspout water for later use. It's the creation of water plazas that are dry most of the year, but are designed to safely flood during heavy rains, becoming temporary parks for water. This approach doesn't fight the water. It invites it in, slows it down, and puts it to work. And then there are the defenses. The levees and floodwalls that line our rivers are the shields of our cities. Modern engineering is making them smarter and more resilient. Movable flood barriers, super levees with wide setbacks, and designated floodways, areas intentionally designed to be inundated to protect more critical infrastructure, are all part of a new approach to flood control. It is an admission that we cannot stop the water everywhere, so we must wisely choose where to let it go. Yet the most profound shift may be a philosophical one. We are moving from an architecture of conquest to an architecture of harmony. The old model was to pour concrete to control nature. The new model is to work with nature's own systems. It's about restoring wetlands which act as natural sponges. It's about setting levees back from the river to give it room to meander and spread out. It's about recognizing that we will never be stronger than the Sky River, so we must become more clever. We are learning to be architects not just of concrete and steel, but of the water cycle itself. We are designing landscapes that can absorb the shock of the deluge and remember it during the drought. We are building a world where the immense power of the atmospheric river is not just a threat to be survived, but a resource to be harvested. We are building the containers for the future, hoping they will be large enough and smart enough to hold the coming storms. The river in the sky will continue to flow. Our task is to ensure that when it falls, it becomes a blessing we can keep. We have traced the journey of the Sky River from its birth over the ocean to its impact on the land. We have measured its power and plotted its course with technology. But the final and most important chapter in this story is not written in data or engineering. It is written in the lives of the people who live in its path. It is found in the quiet rituals of preparation, the jarring scream of a siren, and the shared strength of a community facing down the storm. To live in the shadow of atmospheric rivers is to develop a second sense for the sky. It is a relationship built on respect, memory, and a practiced readiness. The first line of defense is no longer the levee or the sandbag. It is information. The sophisticated forecasts we've explored are useless if they don't reach the people who need them. This is where early warning systems become a lifeline. They are the crucial bridge between the scientist's supercomputer and the family in their home. It begins with a phone alert, a jarring buzz and a message. Flash flood warning in this area. Seek higher ground now. These targeted, location-specific warnings are the fruit of decades of research and technological advancement. They provide the most precious commodity in a disaster, time. But warnings must be understood to be heeded. This is where the work of community preparedness begins, long before the first cloud appears. It happens in town hall meetings where emergency managers explain evacuation routes. It happens in schools where children practice what to do. It's the local meteorologist on the evening news using clear, urgent language to explain the difference between an AR2 and an AR4, making the science actionable. It is also deeply personal. For many, the approach of a forecasted atmospheric river triggers a quiet, familiar routine. It's the trip to the store to stock up on batteries, water, and non-perishable food. It's the act of clearing the storm drains on your street of autumn leaves. It's the conversation with a neighbor. Do you need help putting up your sandbags? These are the small human rituals of resilience. They are a way of asserting control over the uncontrollable, of looking the giant in the eye and saying, "I am ready for you." And then there are the stories. The collective memory of a community is its most vital shield. Talk to an old-timer in California's Central Valley, and they might speak of the Great Flood of '69, of boats rowing down what was once Main Street. In the Pacific Northwest, families have tales of the landslide of '07 that took a home but brought the street together. These are not just stories. They are oral histories that encode vital lessons. They are the reason why one family knows to move their antique furniture upstairs when the river is forecast to hit 28 feet, and why another knows which road is the first to wash out. When the storm hits, these stories of past survival become a guide for present action. The real test comes after the warnings and during the deluge. This is when community transforms from a word on a map into a living, breathing organism. It looks like the community-led evacuation, people with high-clearance trucks checking on elderly residents who live in low-lying areas. It looks like the spontaneous emergence of volunteer sandbagging brigades where strangers become a fast-moving assembly line against the rising water. It sounds like the local radio station powered by a generator becoming the central nervous system for the town, sharing which roads are closed and where help is needed. To live with the sky's rivers is to understand a profound paradox. These events are immense impersonal forces of nature, yet our response to them is intensely, fundamentally personal and communal. The flood exposes our shared vulnerability, but in doing so, it reveals our shared strength. The personal story is always the anchor. It's the young couple watching the creek behind their house rise inch by inch, the memory of their wedding day photos in the backyard making the threat feel surreal. It's the farmer standing in the pouring rain, feeling a pang of guilt for feeling relief as his parched fields drink deeply, even as he fears the erosion tearing at his soil. It's the firefighter, exhausted after a 48-hour shift of swift water rescues, who says, "We don't stop because we're all in this together." This is the final layer of defense. It is not made of concrete or wire, but of empathy, relationship, and a stubborn commitment to one another. The technology tells us the river is coming. The engineering tries to manage its flow. But it is the human spirit, prepared, connected, and resilient, that determines whether a community will be washed away or will weather the storm. The Sky River is a force of nature, but the will to prepare, the courage to help a neighbor, and the strength to rebuild, these are forces of human nature. And in the end, it is this balance between the power above and the spirit below that defines what it truly means to live with the rivers in the sky. We began our journey by looking up, wondering at the idea of a river flowing unseen above us. We have, since then, plunged into its depths, measured its power, traced its paths across oceans and continents, and felt its profound impact on the land and on our lives. We have given it numbers, scales, and names. We have flown into its heart and mapped it from space. But now, at the end, we are returned to where we began, to a sense of wonder. For all our science, all our engineering, all our forecasts, the fundamental truth remains almost mystical. We are all, every moment of our lives, held in the arms of the air. The atmosphere is not empty space. It is a fluid, a dynamic ocean we are submerged in, and flowing through this ocean are these vast, invisible currents, these rivers of vapor that are the great arbiters of life on Earth. They are the circulatory system of the planet, and we and every living thing we know are sustained by its flow. This relationship is our deepest and most ancient context. Long before we understood the physics of condensation, we knew the gratitude for a full cistern after a long drought. We felt the awe and the fear of a rain that would not stop. We told stories of great floods that cleansed the world, and of gods who controlled the skies. In a way, those stories were our first models, our first attempts to explain the awesome power of the sky rivers. Now we have better models, we have data, but has the essence really changed? We still look to the sky with hope and with trepidation. We still wait for the rain. We still fear its arrival when it comes in excess. Our science has not diminished the phenomenon. It has only deepened our appreciation for its complexity and its power. We have not conquered the river in the sky. We have simply learned to listen to its currents. This listening reveals a profound duality. The atmospheric river is the ultimate paradox. It is the bringer of life, the ender of droughts, the builder of snowpack, the filler of reservoirs. It is the reason for the groves of giant redwoods and the fertile valleys that feed nations. Yet, it is also the bringer of ruin, the trigger of mudslides, the breaker of levees, the force that can erase in hours what took generations to build. It does not choose between these roles.
It simply is.
Its character is determined by its intensity, its duration, and the landscape it meets. It is neither benevolent nor malevolent. It is a force of nature, immense and impartial. Our challenge is not to label it, but to learn to live within its rhythm. Our relationship with it, then, must be a relationship of balance. It must be built on respect, not domination. We can no more stop the atmospheric river than we can stop the tide. But we can learn its language. We can build smarter, live more wisely, and prepare more thoroughly. We can restore the natural landscapes that absorb its blows and capture its gifts. We can design our communities to bend with the flood, not just resist it. We are learning to see ourselves not as separate from this system, but as a part of it. The water that falls from the sky becomes the water in our veins. The crops that feed us are grown with its gift. The very shape of our civilizations has been carved by its flow. We are creatures of the river in the sky, just as surely as we are creatures of the land, and so we are left with a quiet humility. The same invisible currents that water our world also hold the power to reshape it. We are suspended between the desert and the deluge, forever dependent on the delicate, powerful balance of the hydrosphere. To know the atmospheric river is to understand that we live on a planet that is alive, breathing and constantly moving water from sea to sky, to land and back again. We are participants in this great cycle. Our fate is literally and metaphorically written in the clouds. So the next time you feel the first drop of rain, or see the news of a coming storm, or watch a river flowing peacefully through a valley, remember the journey. Remember the immense invisible river in the sky that made it all possible. It is a reminder of our connection to something vast and ancient, a force that both sustains us and demands our respect. We are all, always, held in the arms of the air, cradled by the very currents that bring the rain and the sunshine of our lives. It is an embrace we are only just beginning to see, and one we must learn to cherish.